So now, before I start, any questions at all? Okay. Now, we covered basically how to use a Smith chart just to find really the reflection coefficient, the input impedance at any distance from the load, or at the load, or I'm sorry, at the generator, what the load impedance was any distance from. Yeah.
Can you use a Smith chart if like the load impedance is more than like 100 times more than 9? Or either way?
What if the load impedance is what?
More than like 100 times the line? Because like this only goes up to like not very big values.
If you think about this, when you normalize, let's just say it's 1,000,000 ohms, all right, and say the characteristic impedance is 100, all right, so that would be 10,000, right? All right, if you have 10,000 as the value you're putting in, where are you? You're right at the corner. You're right at that almost infinite point, right?
Yeah.
So it wouldn't be useful for that. You'd have to use a software to do that kind of thing. But to be frank about it, nobody would have 1,000,000 ohms with a 100 ohm line. It just wouldn't happen. All the things you're trying to do are things within the range of normalcy, you might say. I mean, it's possible we're going to see you're going to use an open circuit for something today, but it's for a very select purpose of impedance matching. Right? It doesn't. An open circuit has an infinite amount of impedance. There are ranges that this works. You're right about that, as far as I can see. Okay. Any other questions? That's actually a legitimate question. Because I mean, the Smith chart, you could probably figure this. Think before calculators, when slide rules were made to calculate. This was an incredible tool because it allowed you to calculate things very quickly. You're going to see it's still used today for a large number of things, especially what I'm about to show you today. So, are you all good with everything up to this point? If input impedance, reflection coefficient, standing wave ratio, and that's about it for this. Now, today we're going to do impedance matching. This is very important. I want you to listen to me carefully about this part. It's not that apparent in the book. All right, so if I start with a Smith chart, as such, and I try to draw these things as best I can, that's the one circle, and I always show that, right? This would be a point of 0, and this would be the infinite value of impedance if we're plotting it, right? Now, I'm going to come and just explain to you a basic example. If I have a transmission line, as such, it has some characteristic impedance ZL, a load impedance ZL and characteristic impedance Z0. And what I'd like to do is add something to this transmission line so that the reflection coefficient here will be 0, so nothing will be reflected. This is called impedance matching. You all follow the reasoning behind it. The motivation is to add something to this transmission line so there'll be no reflections, all right? We're going to start by adding things in series. All right. That means we're going to find something to put in series here that will allow, at this point over, the actual reflection coefficient be 0, or the input impedance right here is just going to be equal to 1, the normalized input impedance. You follow my train of thought? We'll get to how far away this is placed and everything in a second. All right? Now hear me on this one. Make sure you listen carefully and be attentive, because this can be confusing. My first step is always going to be finding the normalized impedance. That's capital ZL over Z0. You all follow me on that? Now after that's done, I'm going to plot that point, wherever it may lie. I'm just going to pick a point, all right? I'm going to pick it right here. I don't even know what that is, but I'm just showing you. I'm going to pick that point. And this is going to be 0.1, and this is my ZL, normalized. All right? Now, the next thing I'm going to do, I'm going to take a compass, and I'm going to make a circle centered here with that radius. Everybody follow me on this? Now, if I'm here and I look at wavelengths towards generator, I'm moving in this direction, right? Now, there's a point, this is really important. When I intersect this point right here, in other words, when I move from here to here, now I have a point that has just 1 plus jx, right? It has a real value of 1 because it's on the one circle, but it has an imaginary value that's jx, that's normalized. Do you all follow me? If I kept moving along this circle, I would hit what I call a conjugate point that would be 1 minus jx. It would have a real value of 1, but you see where it intersects the one circle, and have an imaginary value minus jx that will have the same magnitude as the x above. You all follow me? Now, if I can add something, if I move from here to here, I'm going to do it this way. From here to here, I'm going to call that distance L1. So if I move to L1, all right, we'll do examples of this, but you need to see the reasoning behind it. Now, I have a value of 1 plus jx, right? If I add minus jx in series, because this is impedance, it gets rid of that imaginary component. Do you all agree with me? Follow me? So if I add minus jx there, and it has to be normalized, and I'll get to that, then the input impedance here is just, the normalized input impedance is 1. It means the denormalized, you might say, would be Z naught, and the reflection coefficient would therefore be 0. Do you all follow me? Now this is series impedance matching in a nutshell. So if we assume that this is a minus jx value, what component has a minus j something value in the phasor or frequency domain? Go ahead. Do you all follow me on that? The capacitor has an impedance of 1 over j omega c, or minus j over omega c. Do you all follow me on this, class? Now, it has to be normalized. Remember, when we went in and used the Smith chart, we normalized the actual load impedance to Z naught. So then you have to divide this by Z naught. And I'll put it here, minus j over omega c Z naught. And set that equal to minus jx. That's what you want. Do you all follow me? Now, if you know the frequency and the characteristic impedance, you can see that I have what? I have 1 over omega c Z naught equal to x, or I have what? I have c equal to 1 over omega times Z naught times x. Y'all follow me on that, class? And that would be the value of the capacitance you would select to put in series with that transmission line to eliminate the reflections. Do y'all follow me? Yes, sir.
What was that under in the denominator?
I think it's something.
I had a comment about my writing being bad. I'm going to try to do better. And I appreciate that you can never really help me enough. But this is 1 over, this is omega, which is 2 pi f. Omega, and this is going to be Z naught, and then the x value. I'm sorry about that. Can you all read it back? I'll try to do better. My handwriting suffered greatly over the years. I don't know why. Now that's a capacitor. You all agree with that? Now let's say we continue. We don't go to L1, but we go all the way over here where we come through here. It's almost a quarter wavelength, right? The way I drew it. But we'll call this L2. Now, if we had the same circuit, I'll draw it down here, same exact value for ZL and Z naught, but now we moved out a distance L2. Now we have to add something in series, right? But here it's 1 minus jx, right? So I want to add plus jx because it's a series impedance. Do you all follow me on that? Let me understand this. All right, let me know too, because if you don't, I need to clear this up right now. So this is going to be a plus jx. And when I add that there, then the normalized impedance looking this way would be 1, the denormalized would be Z naught, and therefore the reflection coefficient is what? Z naught minus Z naught over 2 Z naught, it's 0. That's what you want, nothing reflected. The whole idea is to have nothing reflected, because reflections are very bad in so many ways. It can destroy amplifiers if they're power amplifiers, And you don't want to add any elements that's going to dissipate power, so you're limited to inductors and capacitors and transmission lines. We'll get there next. So what's the value? How am I going to calculate what that is? This was the capacitor, right? Want to take a guess what this is?
Inductor.
An inductor, right? So what's the inductor, what's the impedance of the inductor?
JWL.
J omega L, right? Do y'all agree with that? Just J omega L. But it has to be normalized. So I have to divide by Z naught, because that Smith chart is a normalized value. Y'all follow me? So then I divide by Z naught, and I set that equal to JX, because that's what I want. Now you can obviously see the J's go away. I mean, but I put that there for a reason, so you'll understand step by step the rationale behavior. All right, that means when I look at L, what do I get? I get X times Z naught over omega. It's quite different from this one, isn't it? Here, C is 1 over omega Z naught X. Over there, Z naught's on top, right? And X is on top. You all follow me for an inductor, because we have to normalize. That's an inductor and a capacitor doing impedance matching by being added in series. It is used. It is used. All right, now I'm going to do it with the transmission line. This one you need to be very attentive for. You understand the capacitor and inductor. What I'm about to show you may not understand so well. We're adding this in series. I'll show you what I mean by that. Let me erase this. By the way, I think those YouTube videos cover this. The lady does cover it. She does a great job. How many watched this on the video? She does a great job there, but I'm trying to be clear about this. So now what I'm going to do, I'm not going to do it with an individual element, but a transmission line in series, all right? So I'm going to start up here. It's still going to be attached to L1. And now I'm going to put a transmission line, and this one's going to have a shorted load. And we have to figure out the length of this line. I'll call it L stub, because these are called stubs. And it's going to have a short circuit load. Now please be attentive. Y'all follow me? I'm going to replace that value that was, for the top one, it was minus JX, right? I'll just put this in close. This had to have a minus JX value. Y'all with me? Everybody? So, now watch, be careful of watches. So if I just take a look at a transmission line, and I put a short circuit here, it's got a characteristic impedance of Z naught. What's the impedance of a short circuit? 0, right? There's 0 ohms. What's the normalized value, class?
0.
0 again. Now, on a Smith chart, where is 0? Here. You all see it? Take a look at your Smith charts. That's 0. Now, I need to move on this Smith. Remember, we're already normalized. Y'all follow me on this? We're assuming both the transmission lines have a characteristic impedance of Z naught. We can deal with this later if they don't, but for now, just follow. Y'all with me? So how far do I have to move? Well, I have to move, that would be a half wavelength, right? I mean quarter wavelength, right? I need to move till I get to what? On the outer rim right here, a value, wherever it may be, I don't know where it is, of minus JX. Y'all follow me? Right? Everybody with me on that? Then that input impedance normalized would be minus JX, and when I attached it in series, on this side, you would have a reflection coefficient of 0. You would have just a, yes sir?
Was that already minus JX, or wouldn't you need to add a positive
Yeah,
JX?
well, no, this one was plus JX, we were gonna add, remember I stopped right here on this one?
Mm-hmm.
Let me just be clear about this. For this one, I'm assuming at L1, if I look this way, I would have 1 plus JX. So I have to add a minus JX, that was my point. You all follow me on that, class? Can you all, how many understand this? Be clear. You guys do, all right. So what I need to do is go all the way around. Remember, these values are on the actual rim of this, and it's minus JX. Then the length I would go would be from here, quarter wavelength plus whatever else that is. Y'all follow me? That's if it's short. You got me on this? Short circuit stubs are commonly used. The other option is this. Now I could make it an open, right? An open circuit has how much impedance?
Infinite.
Infinite, by definition, right? What's the normalized value of infinity? It goes along with the thoughts that you had earlier, and you see it. What is it? Infinite, right? If you take infinity by 100 ohms, it's still infinity, isn't it, class? So where's infinity over here? Well, this is where 0 is. Here's where infinity is, at 0.25 wavelengths towards generated. Do you all see that? Take a moment and look, convince yourself. You with me? Now, when I have an open circuit there, I don't really like this for a lot of reasons, because that means there's a plus minus potential there, and there's stray fields, there's capacitive fields around there that can cause a lot of problems to nearby circuitry if it's not careful. They are used, but anytime you have densely packed electronics, I wouldn't use them. That's my advice if you ever have to make a choice. Use shorted always. All right, now for that one, I'm here, and I want to get to here, right? So that's a quarter wave shorter, but do you all understand me? Now I would start here, go to here. The length is going to be a quarter wave less than the first length. Does that make sense to everybody? How many see this? Now that's all series impedance matching with series elements. Most of the time, they're done in parallel. And it's called shunt matching, all right? Now I'm going to erase this, but I'm going to just give you a second to soak it up. We'll do problems on all these things, all right, class? I want to clarify everything. But I want to get all the methods out. But the key thing is in series, you know you're going to move after you come in to the point where you're either at 1 plus JX or 1 minus JX, right? And then you're adding an element, either a capacitor or inductor in series, or you're going to add a transmission line in series, a shorted or open circuit. Those are your choices. But the reason behind doing this is to get rid of that JX. That's the whole deal. Now, next is going to be shunt. This one people tend to mess up a little more. And I don't know how they get my number. I don't know about you, but I get things about my car coverage has gone bad, and now I can get it at a super discount, or I need life insurance, or is my student loan paid off? I'm trying to think of some of the other things. Am I interested in a new car? You guys get this kind of nonsense or not? No? How many get student loan stuff? Anybody? One or two? How many get car stuff? I always wonder what they bother you with. I mean, yeah.
Fat loss pill.
Fat loss, yeah, well, that's what I'm looking for right now. Yeah, that's fat loss.
I'll send you their number.
Fat loss. College students, that's one thing they're usually not worried about. They got so much anxiety and stuff, they don't have a problem. All right, here's my Smith chart. And now, what we're going to do is go back. I'm going to redraw the same problem as before. You guys get stuff about gambling and fantasy football and stuff like that? I'm just curious about that. I have not been inundated with it, but my friends have. Y'all know fantasy football? All right, if you play it one time, they got your number. This is L1. Now, we're going to do this one a little different. We're doing this in the admittance domain. And instead of hooking something in series, we're going to hook something in parallel. So we're going to find something we're going to put there such that on this side of it, you have a reflection coefficient of 0. Do you all follow me? Now please watch this carefully. So, if you're going to hook something in parallel, you work in the admittance domain, which means this. Now watch this. Normally you come in, you know how to come in at ZL, right? I'm going to come at the same point. This is my value of ZL. That's 0.1. But that's impedance, right? Now we're going to go to the admittance domain, which is 1 over ZL. So you're going to come down here, This line will be the same length as that line, and you're gonna put a dot here, and that's 1 over ZL or YL. You can do this on your computer. It'll be at the conjugate point, I call it. All right? Now, do me a favor, think about this. Why am I doing this? This is admittance, right? Normalized admittance. I'm gonna go ahead and I'm gonna circumscribe a circle, or just draw a circle, as I did before. Lousy circle, but I've drawn it. Now I'm going to move from here, whatever this point is here, all the way around till I hit this point where I have 1 plus JX. But it's JX, but it's actually, I should put 1 plus JB or something. This is an admittance, not an impedance. Do y'all follow me, class? I'm still moving to the point where I have, this is, maybe I should just do it this way, so I don't confuse it. This point where it intersects here is 1 plus JB. And I'm putting that there instead of an X so you kind of registers. It's not an impedance. It is an admittance. All right, everybody? Now, when you look at that, if I added something in parallel, remember, admittances add in parallel like series resistors, right? If I had something that knocked that out, so if it was 1 plus JB, if I had minus JB here, it would get rid of it. Do you agree with that, class? So now we're going to talk about admittances. When I have admittances, they're 1 over impedances. So just follow me on this part carefully. If I talk about a capacitor as such, I know the capacitive impedance, I would just call it Z, is 1 over J omega C. Does everybody agree with that? When I take a look at that, and I look at the normalized value of that, it would be 1 over J omega C Z naught. Just dividing that value by Z naught, or it would be minus J, if you like. Minus J over omega C Z naught. Do you all agree with that? Now, if I have an inductor, then the impedance would be J omega L, and the normalized impedance would be J omega L over Z naught. Do you all agree with that? Now, the normalized admittance for a capacitor is really just J omega C Z naught. It's 1 over this. Maybe I should leave the J down there so it's more apparent. It's just 1 over that. Do you all follow me? That's normalized. Correct, class? Can you all follow me on this? The normalized impedance here is going to be what? Minus J omega, right? I'm sorry, minus J Z naught over omega C. Do you all follow me? That would be the normalized impedance of the inductor. Right? Yeah.
On the bottom right, should that be an L? Or is that supposed to be?
Oh, yes. My bad. I'm sorry. That's...
Should it also be positive?
Well, if you go 1 over this, it becomes minus J.
Okay,
doesn't it?
minus.
Right, 'cause typically, this is, if you take 1 over J, you get minus J. Correct, class? Everybody with me? So these two are the keys for inductors and capacitors, right? Y'all follow me? So if we're going to add a capacitor right here, not what? Wait a second. What do we actually need? If we got 1 plus JB here, we want to add minus JB. Do you all agree with that? Minus JB is actually an inductor, isn't it? Y'all follow me? How many see this right here? Think about it. So I would say that minus JB, whatever that B value is, would have to be equal to minus J Z naught over omega L. Now, you can see the minus J's cancel. And you can also see that L itself becomes simply equal to Z naught, right, over omega B. That would be if you were impedance matching with an inductor, and it would be in parallel, so it's in the admittance domain, right? Can you all, how many see this? I know there's like a lot to think about. Really, the thing you think about is if you're in the admittance domain, things are in parallel. If you're in the impedance domain, things are in series. Keep that in mind, you'll be fine, okay? Now, what if I wanted to go from here? This is almost ridiculous because I'm almost back at the same point. But if I went all the way around here to this point, and I wanted to match this point, this is going to be 1 minus JB. Correct, class? Take a moment and think about it. I'm going further, right? I'm almost a full half wavelength around that thing if you look at it, right? Just about. But now, what would I do? This would be L2. Now I'm going to add actually a plus JB, right? Correct? It would be 1 plus J, or 1 minus JB. I have to add a 1 plus JB. You all follow me on this? Okay, so what's that going to be? Capacitor, right? So you're going to have, for the second time, you're going to have J omega C Z naught equal to whatever the JB is. And you can see from there the J's cancel, and I can calculate C in that case is going to be equal to B over omega Z naught. Now keep in mind the rationale for all this. I want to get rid of the imaginary component, be it impedance or admittance, right? I want to get rid of that. So I'm going to add something either in series or parallel. Now I've showed you how to do it with 2 elements. Now I'm going to show you with transmission lines. Now, this part, be attentive to. You're fairly versed in capacitors and inductors. I'm convinced of that. But transmission lines are something that's not. Does everybody follow me on this? Right? Now, does anybody have any questions before I get to the next part? Okay. So the next part's interesting. And this is the most common way that impedance matching is done. And you might want to write that down, like star. Baginski said this is the one that's used all the time. You'll probably be quizzed on more often than not. Quizzed on, tested on. Star, star. Know this. Do something like that. There's one rule that I have that I always believe in. Never put an inductor in parallel because it will short any DC bias out. And never put a capacitor in series if you don't have to because it kills any DC current that could be used for biasing the transistors. Do you all follow me on that? I'll speak a lot more about this in a bit. So now, what we're going to do, should have left this one up here. But I'm going to start from scratch. I want to do this whole thing. I want to make sure you see this. It's the same exact thing as we did with the parallel capacitor inductor. But I want to do this from scratch for a reason. You'll see. So here is my Smith chart. Sorry, 1. Here is my load. My characteristic impedance. I'm going to come out at distance L1. Now I'm going to hook a transmission line in parallel with this. And the transmission line is going to have a length L. It has a characteristic impedance of Z naught, and it is shorted. Y'all follow me? Now, the idea is, we know we're going to move, in the admittance domain, we're going to take ZL over Z naught, find that point, find the conjugate points, or in YL, and we're going to move until I have 1 plus or minus JB here. Y'all follow me? Doesn't matter if it's plus or minus. Now, if we have a short circuit, now we're talking about the stub itself, which is this transmission line. This is called a stub. It's called stub tuning. When we have a stub, and I'm going to put a short circuit on it, it has a characteristic impedance of Z naught, and I'm looking for the length of the stub. Okay? Now, just write that down. Think about this for a second. I am in the admittance domain, right? Yes, sir. This is effectively just putting a short circuit across the transmission line, not the load. Here's the load right here.
Yeah, you put a short circuit parallel to that.
No. Just watch. See, this is a separate transmission line right here that's attached at this point. It's not shorted there. It's attached, it's shorted here at the end. All right, just keep watching, I think it'll make sense. So if this is a short circuit, the impedance here would be 0 ohms. Do you all agree? What's the admittance? It's infinite, right? You all agree with that? What's the normalized admittance? YL normal, it's infinite too. You all follow me in this class? All right, we're in the admittance domain. This is a little unfamiliar territory. You're not used to doing this. So now, when I come to my Smith chart, remember, this is 0 and this is infinity. You all with me? So when you have a short circuit stub that you're going to use, in other words, the load on that stub is shorted, and you're going to put it in parallel, as ours are, it's called stub tuning. I come in here at this point. This is my entry point for the stubs impedance. Stubs, yeah, see, or stub admittance, sorry, why? Right here. Now I'm going to move until, remember, that's, I'll say it's 1 plus JB, okay? 1 plus JB. I'm going to move until I find the minus JB point. And this would be the distance, or the length, and I'll call it L stub here. This would be L stub. Right? I mean, not that length, sorry. This is L1. This would, right here, would be L stub. This length. And then I would attach it in parallel. Now remember, this would have a normalized impedance of minus JB. Follow me on this, guys? I added to this, it's 1 plus JB minus JB, it's 1. Now, if YL is 1, 1 over 1 is 1. ZL, or the Zn, I should say, at that point, is also 1. When we denormalize and multiply by Z naught, we get Z naught at that point. And therefore, the reflection coefficient Z naught minus Z naught is 0 over 2 Z naught. It's 0, nothing is reflected. How many understand that? When you see some problems, it'll become apparent. That is for a short circuit stub, right? Our other the other alternative is an open circuit stub. I don't recommend open circuit stubs for a reason that I mentioned earlier. The minute that's an open circuit, right there, now you've got a plus minus potential. You've got stray electric fields that are around there, and if it's a densely packed piece of electronics, you're going to have problems. Do you all hear me on that one, class? Just remember that. It'll save you a lot of headache if you ever have to use this stuff. And you probably, if anybody's doing, if you're working at a small company especially, you're going to be doing stuff like this. Because when you're at a small company, you can make a lot of money, and the company grows very fast, but you're not going to have one single area like AI that's yours. You're doing everything. Soldering, anything that needs to be done, including doing stub tuning and things like this on components that are going to be used in like radar or stuff like that. All right, now if it's an open circuit stub, here, as I'm showing. Well, the impedance of the load is infinite, right? Right? That means when I take that and I find the actual admittance of the load, it's 0, right? And it would be 0, and it would be Siemens per meter, or 1 over ohm meters, or Siemens, I should say. Now when I normalize that, what do I get? 0 as well. Correct, class? Anytime you have infinity or 0, normalizing them doesn't change the value. So where do I come in at? Well, now I'm over here. Y'all follow me? Now, if I want a value of minus JB like before, now I have to go all the way to here, which is a quarter wavelength plus the stub distance I had from the first part. Y'all follow me? It's longer that way. Everybody with me on this class? You have a cross look on your face. You don't believe me?
Oh, well, I get what you're doing. I just, what's the point of doing the stubs?
We're going to eliminate the reflection coefficient is going to go to 0 when we add this. That's the whole idea, it's matching. Where there's no way that it's going to bounce back. See, if you have a reflection coefficient, it's not 0. Some of that wave that you're sending is coming back in the other direction. And that's nothing but problems for the power amplifier that's causing it. And it's also reducing the amount of power transmitted and everything. Go ahead.
Like, we're trying to fix the radio upstairs. If we have a really horribly matched impedance on our amplifier and crank all 2,000 watts,
Well, you can blow it up too, if they don't have a fail-safe. Anytime you're dealing with power amplifiers and you're feeding things, anytime, like, say you just cut the cord or cut the actual transmission line, now you got a reflection coefficient of 1. Now, literally, the voltage on that amplifier doubles, and it usually causes arc over and components destroyed and stuff like this. Sometimes they have, it's like lightning protection, when all of a sudden they're sensing a voltage that's over a threshold, it'll just short at the ground automatically, throw a breaker. But I'm warning you about this. I have not destroyed a whole lot of equipment, but I've destroyed enough equipment to know how important it is to do impedance matching. When you're young, you're dumb, and you like the really great, I want 500 watts per channel. Boom. Oops. Forgot about that. So now we're going to do some problems. I'm glad I wasn't rich when I was young. I'd kill myself. Okay, so now we're going to do problems. And we could start with probably a simple example in the book, example 2.6 on page 80, just for kicks, and then we're going to keep going. I'm going to get into the stuff doing after this one, but we got at least 10 minutes. So in this one, it says, we construct a simple matching network. Okay, this is on page 80. Help me out here, guys, and I appreciate if you work this with me. Can you get a clean Smith chart, get a straight edge, get your compass, and let's do this together. So here's my Smith chart. And here's the problem. If you have your book, look at it. So he has a characteristic impedance of what, 50 ohms? You tell me if I'm wrong here. And he has a load impedance here of, what is it, 11 plus J25. Let's do this together. We have 11 plus J25. So first thing we have to do is normalize it. Do you all agree with that? So we're going to take what? Find ZL, and he wants this as a series element, so it's going to be capital ZL over Z naught, and that's going to be what? What is that? Pardon? 0.22 plus J, they're all 1/2, right? Or 0.5, let's do 0.5. So if you could, with me, locate that on the Smith chart. So 0.22 is a big old circle, like such, and J.5 is about here, so I'm going to guess that point is about here. Tell me if I'm close. Somewhere out here, and this is going to be 0.22 plus J 0.5, and this is 0.1. Y'all follow me? You agree with that, class? How many agree with that? Right? Now, what's the wavelengths towards general? If you have your book, you can just read it off of his. Anybody?
Like 0.076.
All right, anybody confirm that right here? 0.076 lambda. Anybody?
Yes.
You got it? All right. Now take your compass. I hope you brought one. This is really helpful if you bring your tools. And then get a circle of this radius. Describe it there. Okay? With me? This is the impedance domain. Now, this is 0.1. 0.2 is right here. We know we have a real value of 1. And this is going to be 1 plus J something. Now, if you look, it's like the line that comes like this. What is this? J, like 3 maybe, or 4? I can't remember. Can you take a look, guys? Just look at the trajectory of the line that goes through that point of intersection. Tell me what it is. J what?
J 1.9.
1.9, guys? How many see 1.9? Can you all see it back there? I'm going to say it's J 1.9, so this is J 1.9. Now, we're going to put an element in series that's going to get rid of it, correct? It's got to be minus J 1.9. Make sense to everybody? So we have minus J 1.9 has to be equal to what has an impedance that's got a negative J sense?
Capacitor.
Capacitor, right? So we put down, and I'll do it this way. I'm going to put down the capacitive impedance right here. It's minus J over omega C, but it's got to be normalized. So I divide it by Z naught. Do you all follow me? How many do it? So I divide it by Z naught, and now I can find out both the distance that we'll get in a second and the value. For the value of C, it's going to be what? It's going to be 1 over omega times 1.9 times Z naught. So it's 1 over, what's the frequency of this? 2 pi, is it a gigahertz? Anybody? He has to give a frequency.
Says in drill 2.5, for example 2.6, it must operate at 800 megahertz.
How many?
800 megahertz.
Okay, unfortunately. So it's 2 pi times 800 megahertz, or 8 times 10 to the 8, right? That's 800 megahertz. And then it's going to be times 1.9, and then it's times Z naught, which is 50. So this is the value of the capacitor. Can you give that to me? See if he's right. He probably is. Over 2 times 50 is 100. 200. Oh boy. I don't know. Anybody? He's probably right. Anybody at all? One over 2 pi times 800 megahertz times 1.9 times 50. Anybody?
I got like 2.09 times 10 to negative 15.
Wow.
I might be wrong.
That's extremely small. But
2.09 times 10 to the negative 12.
Yeah.
I got that too.
sounds better. I don't know what the capacitance is.
Okay.
Does he show the value?
He says the answer down at the bottom, the capacitor is 2 picofarads.
Yeah, what did we get?
2.09 times 10 to the negative 12.
Say that again?
2.09 times 10 to
All
the
right,
negative
about
12.
that. 2.09 times 10 to the minus 12, which is about 2.09 picofarads, about 2 picofarads. So we're right. Y'all follow me? Now, does he ask for it to be done with a transmission line too? Because we're going to do it with the transmission line. We're going to do it with a series stub. Hear me? But I'm going to short it. Follow me on this? Now just listen to me. Everything at this point up to here, oh, we didn't get the length of the line. Actually, to get the length of the line, draw a straight line through that point right there and tell me what this wavelengths towards generator is. Okay. Now, the distance, you always go from the place you landed minus the place you came from. So the actual length of this line right here in wavelengths, and it's small, it's going to be 0.183 minus 0.076 lambda. And what is that? Zero point what?
107.
107 lambda? Anybody else confirm? You got that? Now, I don't know what he has in his book, but he has 0.112. It's probably just eye error, you don't see that well. But his answer is probably right, but you understand the method, right? Okay, now that is with a capacitor we would have in series right here. Now we're going to, I'm removing that, and now we're going to do it with the transmission line. Now please listen to this part. So we're going to have a shorter transmission line, and it's in the impedance domain. Y'all follow me? I'm going to I'm gonna put a shorter transmission line, it's gonna look like this, basically. It's gonna be attached here, here's the short, it's gonna come here, and this is the length we look for. This is the L stub here, and that's a short. It's gonna have a characteristic impedance of Z0, all right? We need that impedance to be minus J 1.9 after it's normalized. Do you all follow me on this class? How many do here? Let me see your hands. Okay, so I start with my standard transmission line. I shorted it on purpose. So, and I need to find this length right here. The impedance of this is 0. That means the admittance of this is infinite, and the normalized admittance is also infinite. Do we all agree on that? Right? All right. So now, without, because I'm running out of time here. I think I got 2 minutes. If I look for where I'm coming in right here, because that's where the YL would be infinite. Do you all follow me? You can use these for either impedance or admittance. But that's where it's infinite. Do you all follow me, class? Now, you have to move until you get minus J 1.9, right? Do you all agree? Because the input impedance here is 1 plus J 1.9. We're going to move until, if you look on this line, right about here, you're going to see minus, it's going to be 1.9, but it's minus J 1.9. Can you find that spot? It's on the red. Can you all see it? Now, is anybody having trouble locating that? If you are, just let me know. I'll send somebody. How many see this right now? You can see it. Back there, guys? Yeah.
For the length we found, the 0.107 wavelengths, is that the wavelength on the original one, or is that on the length of the stub?
This right here is the length from here to here. It's the length from the transmission line's load that we're trying to manage to the point of attachment of the stub.
Okay.
All right. We're just moving from here to here. That's all, and that stays the same for both of these because we're just adding a series element. Now, when we have this, now to get the length of that stub, we have to move from here. Here's where the stub would come in, right? Y'all follow me on that? And you have to move to here. What's this distance difference? This is 0.25 lambda. What's this? Can you tell me? Look on your Smith charts. It'd be on the outer rim, you'd have 1.9. You may have to extrapolate, but I don't think so. You need good eyes for this, I know. Bring your glasses if you want. What'd you get? Anybody?
0.335.
0.335 lambda. Anybody confirm that? Anybody?
Say like 0.326.
326?
Yeah.
All right. Check again. 0.326 lambda. I'm not sure actually, but can you all see it? You said 0.325. Did you read that wrong or?
I marked the point as 1.7 instead of 1.9.
What's that?
I put the point at 1.7 instead of 1.9, so
Oh,
it's like,
all right, you understand, you know where you need to check. Anybody else not see this point? All right, what's the distance difference then? L stub would be what? Where I went, right? 0.326 lambda minus 0.25, and what's that length? This is the L stub. Class?
0.076.
0.076? I'm going to tell you one thing at this point that you need to hear me. Anytime you're less than a tenth of a wavelength, it's starting to look more and more like just a couple pieces of wire, not an actual transmission line. You hear me? If you had something that's 0.001 lambda in length, that looks like two pieces of copper attached to a short. It is a short. You all follow me? So normally, when you get down less than this, less than a tenth of a wavelength, let me finish my thought. You will either add an additional half wavelength onto it, so it'd be 0.576 lambda, or you will change the way you match. Instead of having a short circuit, you would use an open circuit stub. Do you all follow me in this class? So normally, when it's less than a tenth of a wavelength, now I'm not going to sting you on this one, but I'm just warning you in the real world. Less than a tenth of a wavelength, it's no longer a transmission line. It's just two pieces of wires. All right, remember that. Go ahead.
That L stub length, is that the length of the entire transmission line? Or just
No,
half?
it's just the stub, right? When I say stub, I mean this portion that we're going to connect on. All right?
The way it's connected, it looks like L stub is only half the length.
No, this is the length of the stuff, it's this length right here. Right?
Right, but it's.
Your transmission line is in series with this. Right? Where are you seeing the half?
Also, is the length of half what you have drawn. And it may just.
No, you're looking at, this is the length, this is a coax cable. All right, coax cable, you literally, you're short out from the inner core to the outer,
Yeah, that's-
cylindrical cover. Y'all follow me? Yes, sir.
On the last section, the J, 1.9, so on that, would that be where J 1.9 intersects the circle with
If you,
radius?
no, hold it. Listen, it's a great question. You said, where am I getting J 1.9? When you're traveling on this constant magnitude reflection coefficient, we hit here, if we would just look at the input impedance there without anything, it would be 1 plus J 1.9 times Z naught, right? That J 1.9 is what we have to get rid of. So we get rid of it by adding an element, either in series or parallel. And that's what the goal with this is.
So I think I'm getting a different value.
For what?
The angle,
Well, hold it. Are you getting a different value here?
no, on the negative change.
Here, where do you get it?
I think I'm getting one.
Say again?
0.317.
Okay. I'm not sure the right answer, but, can you bring that up here? I'll tell you the problem. I'll give you the right answer. I think these guys were right, with whoever was saying this, 0.326. I think that's right, but I don't know for sure. I'm gonna take a look at yours. And you guys are dismissed. I'm holding you. I don't mean to, but you can stay if you want. I'm just gonna take a look at these guys. Let's see.